Ladies and gentlemen, we are back with another episode of our hit Solve It series, where you will get complete past paper solutions with explanations that a mere mark scheme or examiner report will not give you. It'll be a quick revision of the entire syllabus, and with a look at the latest paper formats, it will equip you with all that you need to ace your next exam. So, without further ado, let's get started. Assalamu alaikum everyone. This is Fahd Ansari and I'm here to help you conquer chemistry. Now before we begin this video, just a reminder that a whopping 89% of you have not subscribed. So please, if you're one of those people, do press the subscribe button and press the bell for notifications. Let's get right into it. So today we'll be looking at the October-November 2022 paper 1 variant 2 of the AS level chemistry syllabus. This is the multiple choice paper. And this is, as we all know, the toughest out of the AS level chemistry papers because you need to do a lot of working for just 1 mark. But no need to fear. I'm going to help you through this paper. So without further ado, let's get right into the questions. So the first question is, why is the first ionization energy of phosphorus greater than the first ionization energy of silicon? Now, if you look up the periodic table, phosphorus has a proton number of 15, and silicon over here has a proton number of 14. So they're right next to each other in the periodic table. And if I write down their electronic configurations, phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. All right. And silicon over here is going to be just 1 electron less. So we write the same things in the beginning. The only difference is that the last subshell will have 2 electrons rather than 3. All right. So now over here, you can see that we have the shielding electrons in the 1s, 2s, and 2p subshells. So that's a total of 10 shielding electrons. And if you look at silicon atom, we have the same situation over here, 10 shielding electrons. So we have the same shielding effect in both atoms. And we can see that the outermost electron is in the 3rd principal quantum shell, right? In both phosphorus as well as silicon. Then what's different? The difference is that phosphorus has a higher proton number. It has 1 more proton than silicon. It has a higher nuclear charge, so it attracts the outer electrons more towards itself, and that is why option A is going to be correct in this case. Phosphorus atom has 1 more proton in its nucleus. That is why it has a first ionization energy that is greater. So now moving on to a moles question. So we have sodium peroxide over here reacting with carbon dioxide to give you sodium carbonate and oxygen gas. Now the question says that which mass of sodium peroxide would be required to remove 2.4 cubic decimeters of carbon dioxide from the atmosphere at room temperature and pressure. So whenever room temperature and pressure comes up, we know that 1 mole of a gas, any gas, is going to occupy 24 cubic decimeters. So if I have 2.4 cubic decimeters of carbon dioxide over here, what will be the moles of carbon dioxide? So I could just cross multiply these 2 ratios, and it turns out that X equals 2.4 divided by 24, and that gives me 0.1 moles. All right. Now these are the moles of carbon dioxide. You can see that sodium peroxide and carbon dioxide have a 1:1 molar ratio. So this will also be the same as the moles of sodium peroxide. We will also have 0.1 moles of Na2O2. Now the next thing to do is to find the mass. So that is easy enough. We can find the MR of sodium peroxide first. That's going to be 2 times 23. That's the AR of sodium plus 2 times 16, which is the AR of oxygen. So this is going to give us 78. And so we know that 1 mole of sodium peroxide has a mass of 78 grams. So what will be the mass of 0.1 moles of sodium peroxide? So we can just cross multiply this, and Y will end up being 78 times 0.1, and that turns out to be 7.8 grams. And so that's going to be option C that is going to be correct in this case. Now over here we need to find out the species where the numbers of protons, neutrons, and electrons, all 3 subatomic particles, their numbers are different, right? So we can easily eliminate aluminium over here. The reason is that this is an atom, so the number of protons will be equal to the number of electrons, all right? Now, if you look at option B, now over here you can clearly see that the number of protons and neutrons is different because protons you have 17, that's the proton number over here, and the number of neutrons is 35 minus 17, the upper number minus the lower number, that's going to give you 18. Now the thing is that the number of electrons over here, because of this negative charge, you're going to have 1 more electron than the number of protons. Because you have 17 protons, you're going to add 1 to this to get an overall negative charge. And so that is 18. That is the same as the number of neutrons. So this is out as well. Option C, we can clearly see over here that the proton number and neutron number are going to be the same. Don't believe me? Check this out. 32 minus 16, upper minus lower number, that gives us 16. Same as the proton number. And so this is gone, and we are left with option D. That's the only one left. Now, just to verify, number of protons over here, the lower number is 19. Neutrons, we have 39 minus 19. That's going to be 20. It's different so far. And number of electrons, now because we have a positive charge, we're going to have 1 less electron than the number of protons. So that's going to be 19 minus 1, that gives us 18. So you can see that protons, neutrons, and electrons all are different. So it's going to be option D. Now this question over here is another moles question, but this is not as easy as it might look. All right. So we need to take this stepwise. We need to have a structured approach to this question. So listen up. Over here we have 2 reactions. We have a mixture of calcium oxide and magnesium sulfide that react with hydrochloric acid. Now it says a mixture of these 2 compounds, X, that's the mixture, reacts with exactly 0.125 moles of dilute hydrochloric acid. Now, one thing that some students might be tempted to do is to think that the calcium oxide and magnesium sulfide react with the same amount of hydrochloric acid, so they might divide these moles by 2 to get the moles of acid reacting with each of these compounds. But that's not the case. You're assuming then that the moles of calcium oxide and magnesium sulfide would be equal, but that does not have to be necessarily the case. So you move on to the next bit of information. It says the amount of hydrogen sulfide formed is 0.025 moles. If you look at these reactions, only the second equation has H2S involved. All right. So using these moles, we can actually find out the moles of magnesium sulfide. You can see over here that these 2 guys are in a 1-to-1 molar ratio. So you can see that the moles of magnesium sulfide, that's going to be 0.025 moles, right? But that's not what we need, is it? We need to find the mass of calcium oxide. So it doesn't make much sense to find the moles of magnesium sulfide. We need the moles of calcium oxide. So here's the thing. We're going to be looking at the moles of acid here. Now, we know that magnesium sulfide reacts with 2 moles of H+. In other words, this is 2 moles of HCl. All right, because we know that 1 mole of HCl contains 1 mole of H+ ions. So we look at the ratio between HCl and H2S, and that is 2:1. All right. So if I have 0.025 moles of H2S, what will be the moles of HCl? Cross multiply, and that will turn out to be 0.025 times 2, and this will become 0.05 moles of HCl. All right. So now you found out the amount of HCl that has reacted with magnesium sulfide. We can now use this to find the moles of HCl reacted with calcium oxide. So this is the total. All right. And what we're going to do is from this total, we're going to subtract the moles that reacted with MgS, right? This is what reacted with magnesium sulfide. And we're going to get the moles of HCl that react with calcium oxide. So this turns out to be 0.075. This is what reacted with calcium oxide. Now you can clearly see over here that the moles that reacted with MgS and the moles that reacted with CaO are different. They're not the same. And so that's why dividing the moles of HCl by 2 in the beginning is not a good idea. All right. So now that we have 0.075 moles of HCl, we look at the molar ratio between HCl and CaO. All right. We can see that 2 moles of HCl react with 1 mole of CaO. Now, if I have 0.075 moles of HCl, how many moles of CaO will react with it? So the answer is pretty simple. Y is going to be 0.075 divided by 2, and that's going to be 0.0375 moles. All right. Now these are the moles of calcium oxide. Now we need to find the mass. So for this, we first need the MR of CaO. That's going to be 40.1 for calcium plus 16 for oxygen. That's going to be 56.1. And so what we can easily do now is multiply the moles by the MR. So that's going to be 56.1 times 0.0375, and that's going to give us 2.1 grams. So this is our final answer, and option B is going to be correct in this situation. Now we have a redox reactions question in front of us. All right. It says 2 moles of VO2 with a positive charge. These ions react with 1 mole of zinc atoms. So let's write this down. We have 2 moles of VO2 with a plus charge. And this reacts with 1 mole of zinc atoms in the presence of dilute acid. All right. So we have some dilute acid. We don't know how much, but I'm just going to write a blank in front of it. Add H plus means that is this dilute acid. And the products include Zn2 plus ions. All right. So 1 mole of zinc atoms is obviously going to give us 1 mole of Zn2 plus. And an ion Y. All right. Ion Y contains vanadium. All right. So now here's the thing. We need to find out what the oxidation state changes are, because it says over here that only zinc and vanadium change oxidation state. So over here you can see that zinc is going from 0 to +2, right? Zinc goes from 0 to plus 2, right? So that is a gain of 2 in the oxidation state. Now for vanadium, we know that there are 2 moles of vanadium over here. And we need to find out the oxidation state of vanadium first. So we know that this is oxygen 2 times negative 2. Vanadium, let's say this is X. And these add up to give us the charge on the ion, which is plus 1. All right. So if you solve this equation, X turns out to be plus 5. So vanadium is going from plus 5 to something. All right. And we know that there are 2 vanadiums. All right. And we need to make sure that the drop in the oxidation state is equal to the rise in the oxidation state of zinc. So it has to be minus 2. All right. Now, if I have a vanadium that goes from plus 5 to plus 4, that is a change of minus 1. But because there are 2 vanadiums, it's going to be 2 times minus 1. That gives us this minus 2 over here. That's equal in magnitude but opposite in sign to the plus 2 for the zinc. So now we can clearly see that the vanadium is going to have a plus 4 oxidation state. So from these options, we find out the ion containing vanadium that has a plus 4 oxidation state for vanadium. Now, using the same method up here, we can have vanadium over here that is also plus 5. So this option is out. Over here, the vanadium, well, this is going to be plus 3. Again, out. This over here, though, if I look at this in detail, this is Y. And we have plus minus 2 for the oxygen atom. This is going to add up to give us plus 2, right? The overall charge. And so Y turns out to be plus 4. So option C is going to be correct, and we're going to have 2 VO with a 2 plus charge. All right. And we don't even need to bother with balancing the rest of the equation. We don't need to bother with the acid or whatever it is. But let's suppose there was a question that asked for the complete equation. Now what? So over here, if I balance out the number of oxygen atoms, on this side, I have 4 oxygen atoms. And on the other side, I'm going to have 2 of them. So to balance out the number of oxygen atoms, I can have 2 water molecules. All right, because we have acid as well. We have H plus that combines with the oxygen atoms missing to give you water. And so over here we have 4H, and so we will have 4H plus over here, and that will balance out the entire equation. All right, so another question on redox reactions, or at least that concept. So it says the compound potassium bismuthate 5, KBiO3 is a powerful oxidizing agent. What is the significance of the 5 in potassium bismuthate? 5. Now the thing is that whenever we have a Roman numeral after the name of some ion, all right, this is actually the name of the BiO3, all right? And all of this has a negative charge because obviously the potassium from group 1 has a positive charge. And so over here, if you do the calculation, the oxidation state of bismuth, X, plus 3 times the oxidation state of oxygen, which is minus 2, that's going to be minus 1. And so X turns out to be plus 5, same as this Roman numeral. So all that is telling us is the 5 is the oxidation number of the bismuth atom. So now over here we have the decomposition of hydrogen peroxide into water and oxygen. Now it says the reaction is faster when the catalyst is present. Which statement is correct? So option A says the catalyst alters the Boltzmann distribution so that the reactant molecules have more energy. That's false. The reason is that catalyst has no effect on the energy that the molecules already possess. All right, that's the role of temperature, not a catalyst. So option B, the catalyst has no effect on the value of Kc. That is actually correct. All right. And the reason why is because catalyst has no effect on the yield of product, right? So catalysts have no effect on product yield. They do not shift the position of equilibrium any further to the right or to the left of wherever they were already. It just means that the equilibrium, the state of equilibrium, is achieved faster. All right? The position of equilibrium is only altered by other factors like temperature, pressure when it comes to gases, concentration, these kinds of things, not the catalyst. And so obviously if option B is correct, option C is going to be incorrect. All right, because these two statements contradict each other. And the catalyst provides a different reaction mechanism. Well, that is true up till this point. With a higher activation energy, no. It's going to be a lower activation energy. That's how it makes the whole reaction faster. Otherwise, there's no point of a catalyst. So option B it is. All right, now we have a question involving calculation of equilibrium constant Kc and a graph of the concentrations of the product and reactant of a reversible reaction. So let's draw that table. All right. So what we do in such questions where we have to find equilibrium concentrations is we draw a table. Q and R, these are the substances. And we write the concentrations at the start and the concentrations or the amounts that were either reacted or produced and the concentrations at equilibrium. So at the start, you can see that Q has an initial concentration of 0.5. So I'm going to write this over here. And when equilibrium has been reached, concentration of Q has fallen to 0.25. So in other words, that means that for Q, 0.5 minus 0.25, that is 0.25. That is the concentration of Q that was reacted and converted into R. All right. Now R in the beginning has 0 concentration. Now if 0.25 mole per cubic decimeter of Q reacts, we know that the ratio between Q and R is 1:2. So we will have 0.25 times 2, which will be the produced concentration of R, according to that ratio. So that will be 0.5. And so at equilibrium, we will have 0.5 mole per cubic decimeter of R. Now that we have these equilibrium concentrations, the next thing is to write the Kc expression. We have the concentration of R, that is the product, because we have 2 moles of it over here. So this is going to be squared divided by concentration of Q. So we plug these in. This is going to be 0.5 squared divided by 0.25. And so this works out to be 1. All right. So that automatically eliminates options B and D because the Kc is incorrect. Now for the graphs, you can see that Q starts at 0.5, which is correct over here, but it has to fall down to 0.25, and that's exactly what it does. It falls down to 0.25. But for R, it's supposed to start at 0, okay? And it's supposed to end at 0.5 over here. It is ending at 0.25, which is less than the 0.5 moles per cubic decimeter we need at equilibrium. So option A is out and option C is in. All right, you can see that the curve for R ends at 0.5 mole per cubic decimeter. That's exactly what we need. Now a simple question on a reaction pathway diagram. It says over here which statement is correct. It says the activation energy of the reverse reaction is plus 80 kilojoules per mole. Now over here, first of all, we have the reactant energy level here and the product energy level. Now, if I'm talking about the reverse reaction, I have to read this backwards. All right. The products are going to be converted to the reactants over here. And so the difference between the product energy level and the peak of the curve, this is going to be your new activation energy for the reverse reaction. And so you're going to add up these two values, 50 and 30. And so 50 plus 30, that gives us plus 80 kilojoules per mole. That is the unit used on the y-axis. And so option A is in fact going to be correct. We don't even need to look at the rest. All right. Now, this is kind of related to the previous question. We're going to use, again, the reaction pathways, all right, to determine activation energies. Now, for the first pair of reactions, you can notice that W and X are reverse of each other, right? So over here, W, we have sodium hydroxide reacting with HCl to produce salt and water. In X, we have the salt and water producing sodium hydroxide and HCl, right? So we can see that the forward reaction, W over here, this is exothermic. All right. So I'm going to plot it like this: reactants, peak, and then products are going to be below the reactants because this is exothermic. And so you can see that the activation energy for W, this is the activation energy for W, the forward reaction. And for X, the backward reaction, this is going to be going from products back to reactants. So from here, the product energy level all the way up to the peak, this is the activation energy for X. So now it is talking about the activation energy. So X is greater than W. So that means options A and B are now under consideration. C and D are out. Now let's look at the next one. So you can see over here that Y, the forward reaction where HI decomposes to hydrogen and iodine, is endothermic, right? So I'm going to draw the reaction pathway like that. So reactants with a lower energy level than the products. And for the forward reaction, the activation energy is this, right? From the reactants to the peak. So this is EA for Y. And for the backward reaction, going back from product to reactant, we have the difference between the peak and the product energy level. This is going to be the activation energy for Z, the backward reaction. So you can see that over here, Y is greater than Z. All right, so Y is greater than Z, so that's going to be option B. That is correct. All right, so another question on equilibria. It says over here that we're talking about the Haber process. We have been given the conditions. We've been given the partial pressure of nitrogen and hydrogen. And we have a temperature and catalyst over here that says if all other conditions are kept the same, which change will result in a raised activation energy. Now, whenever this term activation energy comes up, you have to immediately think about the catalyst. The reason is that all other factors, including pressure and temperature, have no effect on the activation energy. All the effect is the number of molecules having energy beyond activation energy, right? But they don't change the activation energy itself. So over here, the only option that talks about the catalyst is option B. The iron is removed. You have no catalyst. Obviously, it's going to result in an increase in the activation energy, and that's going to be our answer. All right, so we have an interesting looking compound over here. All right, now we can just draw a simple structure for this. So what I'm going to do is I'm going to split this over here. All right, now AlCl3, you guys are already aware of this structure. It's part of the syllabus, right? You have 3 single covalent bonds between the 3 chlorine atoms at the central aluminium. All right. And for nitrogen over here on the other side, it is bonded to 3 methyl groups. So obviously it can only have single bonds with those methyl groups. Now we have to bring these two together somehow. All right. Now the thing is that the aluminium has an incomplete outer shell. It has an incomplete outer shell at this stage before the bonding occurs. But the nitrogen over here has a lone pair that it can use to form a dative covalent bond, right? Or also known as a coordinate bond between the nitrogen and the aluminium. And so the molecule is complete. And so out of these guys, option D is going to be correct. The molecules contain coordinate or dative covalent bonding. The other word is dative covalent. Let's see why the other options are incorrect though. Option C says the bonds around the aluminium atom are planar. That's incorrect. Aluminium is surrounded by 4 bonds and no lone pairs. So when we have 4 bonds and 0 lone pairs, that actually leads to a tetrahedral shape, not planar. So option C is incorrect. Option B, the aluminium atom in this molecule has an incomplete valence shell of electrons. That was the case before the dative covalent bond was formed, but once it is formed, the outer shell is complete. And so option B is incorrect as well. And it says over here that these molecules attract each other by hydrogen bonds. Well, no, they don't. The only highly electronegative atom over here is nitrogen, and it is not directly bonded to any hydrogens. So there is no hydrogen bonding. And so option A is also kicked out. And so that's going to result in option D being correct. All right, so over here we have an ozone molecule. Now its shape is not part of the syllabus, but we could still figure something out. Now over here, you can see that around the central oxygen atom, we have 1 lone pair and we have 2 bonds. All right, so we have 3 entities, 1 lone pair and we have 2 bonds. All right, so that is 3 in total. All right, now if you recall, the only other situation in which we have studied about 3 entities is about 3 bonds and 0 lone pairs. In that situation, you're going to have a trigonal planar shape. And that's going to give you a bond angle of 120 degrees. Now over here, if you replace one of the bonds with a lone pair, we know that lone pairs repel more. And so as a result, the 2 bonds over here and over here will have to squeeze in a little. So the bond angle will be less than 120 degrees. And so out of all of these options, the most reasonable option to me seems to be option C. All right. Because option B and option A represent tetrahedral and trigonal pyramidal shapes, respectively. So we're not going to go for those. All right, so we need to show which gaseous substance amongst these is going to be more ideal than the others. Now I'm going to immediately remove option B because hydrogen chloride has permanent dipole forces, PD forces, and we know that ideal gases have to have minimal or actually 0 intermolecular forces. So we're going to consider the other options, all of which have only instantaneous dipole, induced dipole forces. Now out of these guys, you can see that if you compare carbon dioxide and oxygen, they're at the same temperature, but you can see that carbon dioxide is at a lower pressure. So we know that higher temperature And lower pressure means that you're going to have negligible intermolecular forces and negligible volume of the individual particles, because the particles will be so far apart. The occupied volume will be much greater than the volume of the particles themselves. So over here, keeping temperature the same, the lower pressure means carbon dioxide will be more ideal. Now, if you compare it to nitrogen, it has the same pressure over here. But the nitrogen is at 1000 Kelvin. So you have that low pressure and a higher temperature. And so nitrogen will in fact behave most ideally given its own intermolecular forces and the fact that it's at a higher temperature and lower pressure. Now this question over here, this is a gimme, right? This is one of those rare, easy questions that even an IGCSE student can answer, right? Which graph represents the variation of pressure P and volume V of a sample of an ideal gas at constant temperature? So you guys are all aware of Boyle's law, that pressure is inversely proportional to volume. So this curve over here is going to be correct. As you increase the volume, the pressure is going to decrease, and it's going to be in the form of a curve, not a straight line. And so that's why option A is going to be incorrect, and so is option C, because the curve has to flatten out eventually. It's not going to get steeper. All right, this is the shape of the curve, option D, that you guys have come across before. All right, now we have another energetics question, but this one is much harder. The reason is that you have been given all of this data, right? For all of these reactions over here, you've been given the delta H, and you've been given some bond energies for these particular bonds, all right? And you need to find out the enthalpy change for this reaction. Now, looking at all of this data can be overwhelming. You might be drawn into thinking about all these complex formulas and everything, and how to draw the Hess cycle, and how this is going to be done. But you don't need to think of it that way, because it's actually pretty simple if you think about it, right? Here's how. Take a look at this equation. We have carbon atoms in the gaseous state and hydrogen atoms in the gaseous state. These are coming together to form ethane, all right? So what is happening is that these two individual carbon atoms are forming a carbon-carbon single bond, and each carbon atom is forming 3 carbon-hydrogen single bonds. And so, as a result, what is happening is that bonds are being formed in the gaseous state, right? Now, what's the definition of bond enthalpy? Basically, it's the energy required to break a mole of a certain bond in the gaseous state. You can see that the product is gaseous, and so these gaseous atoms over here, the carbon and the hydrogen, are being brought back together in that same gaseous state. And so we're going to have the energy equivalent to the bond energies of the carbon-carbon single bond and the carbon-hydrogen single bond that are being released. All right. Now for the carbon-carbon single bond, we have 350. That is easy enough. All right. So we will have 350 over here. There's only one of this particular bond, and so we're not going to multiply by anything. Now for the carbon-hydrogen, we have 1, 2, 3, 4, 5, and 6 of these, right? So this will be 6 times, what will it be? Now here's the kicker. You don't have a bond energy for the carbon-hydrogen single bond. Now that's where all of this information comes in, but you have to be smart about this and actually select the important information. Now, if I look at the third equation over here, we have methane over here, CH4, in the gaseous state that is being converted into gaseous carbon and hydrogen atoms. In other words, the 4 CH bonds over here in methane in the gaseous state are being broken down. So the delta H over here is actually equal to 4 times the bond energy of the carbon-hydrogen single bond, because these bonds are being broken in the gaseous state, and that's what the reactant is in. All right? And that is giving you gaseous atoms that are separated from each other. All right? That is exactly what we want. And so delta H over here is 1648. So we can equate this to 1648. So when we divide both sides by 4, we are going to get the bond energy of the carbon-hydrogen single bond, which turns out to be 412. So now this is the value that you're going to plug in over here, 6 times 412. Now, for all of this, you need to be careful. There's a negative sign over here because these bonds, the carbon-carbon single bond and the 6 carbon-hydrogen single bonds, they are all being formed. And we know that bond formation is exothermic. Bond formation is always exothermic. And so when we calculate this, we get option A as our answer. Now over here, simple question on period 3. Says over here that element X requires strong heating to react with oxygen, and it reacts with chlorine to give a covalently bonded chloride. Now this automatically rules out options A and C because these metals react with chlorine to form an ionic compound. Now, with regards to phosphorus and silicon, which of these will be the answer? Now the thing is that both of them are going to give you the covalently bonded chloride, but the thing is that phosphorus, you should know, this is more reactive than silicon. And so that is why it does not need that strong heating to react with oxygen, but silicon does. And so this is going to be option D. All right. One reason you can give for this is because silicon itself has a giant molecular structure. And so it is unreactive. It takes more heat to react with oxygen. So option D it is. Now over here we have 3 metals in period 3, sodium, magnesium, and aluminium. You can see that the melting point is increasing. It's increasing across the period. Now what is the reason for this? All right. Now the change in first ionization energy, nope, that cannot be the reason because we're not doing a reaction here. Okay, we're not converting these into ions. Option B, the increase in electronegativity from sodium to aluminium, again, not related to a reaction, we're just melting the metals. Option C, the increase in the AR of the elements from sodium to aluminium. Well, that is true that the AR increases, but is that the actual reason? Let's look at option D. The increase in the number of outer electrons in each atom from sodium to aluminium, that is in fact the correct answer. The reason is that metallic bonding, guys, please remember, it's the bond between the positive ions and the C of the delocalized electrons. If per atom you have more delocalized electrons being released, all right, so there's going to be a greater force of attraction per ion in the lattice. And so the melting point is going to go up. So it's going to be option D. Now this question over here is a killer. All right. Now over here you have the nitrates of beryllium, calcium, magnesium, and strontium. They all decompose in the same way. All right. These are group 2 metals. And we know that the general formula for group 2 metal is NNO3, 2. Right. Now these decompose. We get 3 products: the metal oxide and nitrogen dioxide and oxygen. And this is the general equation for all group 2 metals. Now it says over here when 2 grams of one of these anhydrous nitrates is decomposed, 1.32 grams of gas is produced. What is the nitrate? All right. So we have 2 grams of a nitrate, okay? Now, what we can do is we can find the moles. we can divide the mass by the MR. Now the problem is that for each of these nitrates, the MR is going to be different because you have a different metal. So what we can do over here is we can assume that the AR of the metal itself is X, all right? And then we can add up the ARs of the other atoms. So this is going to be 2 for the nitrates, 14 plus 3 times 16 for those atoms, all right? Now here we have the moles, all right? Simplify this. This is going to be 2 divided by X plus 124, all right? Now, what we will do next is to find the moles of gases, the moles of each gas, and then convert those moles of each gas into masses. All right, and then add those masses up for the nitrogen dioxide and the oxygen and equate that to 1.32. So for nitrogen dioxide, the mass of nitrogen dioxide, this is going to be 2 times the moles of the nitrate. That's the ratio between the nitrate and the nitrogen dioxide. That's 1:2. And once we have the moles of NO2, we will multiply by the MR. And the MR is 14 plus 2 times 16. All right. And this actually turns out to be 46. Now, if I do the same thing for oxygen, now the ratio over here, you can see this is 1:1/2. So what I'll do is I'll multiply the moles of the nitrate by half. This will give us these moles of oxygen times the MR of oxygen, which is 32. Now what I will do is I will add all of this up, right? And this will be equated to the total mass of gas, which is 1.32. So let's do this. So we have 2 times 2 times 46 plus half times 2 times 32. Now notice that in both expressions for the mass of nitrogen dioxide and oxygen, we have the same denominator, x plus 124. So I'm going to combine all of this calculation with one denominator, which is x plus 124, and this will be equal to 1.32. All right. Now, if you simplify this further, 2 times 46, that becomes 184, plus half times 2 times 32, that's just 32. So that's 216, and that is equal to 1.32. Now I'm taking this denominator, x plus 124, multiplying it with the other side, and that's going to be x plus 124. All right. Now, once I do this, I need to make x the subject. So x is going to be 216. I will take this 1.32 to this side. So this will be divided by 1.32. And from all of this, I will subtract 124. And that gives me 39.6. This over here, once again, is the AR of that unknown group 2 metal M. Now what I'm going to do is I'm going to go to the periodic table and compare the ARs. All right. So for calcium, it is 40.1, close enough to 39.6, and that's what I'm going to go with. And that's going to be my answer. Now this approach over here is important because it saves you a lot of time from trying out all of these 4 options and looking at their MRs differently and doing the calculation and seeing whether the masses of the gases that you calculate will add up to 1.32 or not. That will waste a lot of time. You could just keep the X, the AR of the metal as the variable and solve for X and then compare from the periodic table. Moving on to the next question. We have 4 solutions over here, W, X, Y, and Z. And you can see over here that we have a constant volume of 25 cubic centimeters. And in 2 of the solutions, you have barium chloride. And in the other 2, you have magnesium chloride. So to the first 2 solutions, you are going to add sodium hydroxide. So what happens is that the barium chloride gets converted into barium hydroxide, and the magnesium chloride gets converted into magnesium hydroxide. So about the first two test tubes, it is asking us which of them has the higher pH at the end. So the thing is that we know that down the group 2, the solubility of the hydroxides increases. And so out of magnesium and barium hydroxide, it's going to be barium hydroxide that has a higher solubility. And so W is going to have a higher pH. So we're going to be considering options A and B now. Now for the test tubes Y and Z, what we're going to do over here is add sulfuric acid. So what happens now is that the chlorides of the group 2 elements will be converted into the respective sulfates. Now for the sulfates, we know that the solubility trend is the opposite. Down the group, the solubility of the sulfates decreases. And so we know that barium sulfate will be less soluble, and so we will have a greater mass of precipitate in Y. So option A is going to be correct in this case. Now, what is the oxidation state of the chlorine-containing species that kills bacteria in drinking water? Now, you need to remember this, that when you react chlorine with water, it's going to produce two acids. It's going to produce HCl and HClO. Now, it is the ClO ion over here, and this contains a negative charge. The H contains a positive charge. This ClO negative is what kills the bacteria. And so over here, what we could do is keep the oxidation state of chlorine as X. For oxygen, it's going to be -2. We add these up and equate to the charge on the ion, which is -1 over here. This -2 belongs to the oxygen. And so we solve for X, and X turns out to be +1. And so +1 is the answer for this. Now over here we have a long story, so let's read through this carefully. So it says the compound Q is a white crystalline solid which dissolves easily in water. Okay, so it's soluble in water. All right. So when concentrated sulfuric acid is added to a dry sample of Q, steamy white fumes are produced. All right. Okay. So over here, whenever we see the word concentrated sulfuric acid, we can think of it behaving as an oxidizing agent. All right. And the situation in which you've seen this as an oxidizing agent is when the concentrated sulfuric acid reacts with hydrogen halides. And the hydrogen halides are first produced when the concentrated sulfuric acid first reacts with the halide salts, right? And the steamy white fumes that are produced when the salt reacts with the concentrated sulfuric acid is the hydrogen halide. And this can further react with the concentrated sulfuric acid in a redox reaction to produce a range of products. Now it says when these white fumes are passed into aqueous silver nitrate solution. All right, so this is where it's different. A white precipitate forms. All right. Okay, so we know that a white precipitate forms with aqueous silver nitrate when we have chloride ions present. All right. And it says over here, this precipitate is soluble in dilute ammonia solution. So that just tells us that the precipitate is silver chloride. It is soluble in ammonia, but it is obviously insoluble in water. That's why it's a precipitate. So we have chloride ions. All right. Now, out of these options, we're going to eliminate option B and option D. We're left with options A and C. Now we know that option A, silver chloride, is a precipitate. It does not dissolve. And we know that compound Q dissolves easily in water. It is soluble. So it has to be option C here. So now over here we're talking about R, a solid which fizzes when hydrochloric acid is added. Okay. And R reacts with hot aqueous sodium hydroxide, giving off a gas which turns red litmus blue. So a gas which turns red litmus blue, this is obviously going to be ammonia. So that means that R contains ammonium ions. And it says that R fizzes when hydrochloric acid is added. So the only anion that causes fizzing when an acid is added has to be the carbonate, right? And carbon dioxide is the gas that is produced, and that is what causes the fizzing. So it has to be ammonium carbonate, all right? So now over here we have multiple options. It's not going to be D because that is sulfate. It's not going to be A because this is the incorrect formula. You have to balance the positive charge of ammonium with the negative charge, the 2 negative charge of carbonate. So it has to be option B over here. Option C is also incorrect because hydrogen carbonate, HCO3, actually has a negative charge, 1 negative. And so it's not going to be 2 ammonium ions over here. That would just be 1. All right. If that would have been the case, then it would have been a tie between options B and C. But because this formula is incorrect, we're going to go with option B. So photochemical smog is a type of air pollution produced in urban areas by the effect of sunlight on substances released from vehicle exhausts. Which mixture of primary pollutants leads to the formation of photochemical smog? So questions on smog haven't come up very often in the past, but this is a very simple question. All right. So we definitely need unburned hydrocarbons. All right. So we're only going to be considering options B and C at this point. And out of these two guys, carbon monoxide or nitrogen oxide. So remember that there are 3 things that are important, right? You need oxides of nitrogen, you need unburned hydrocarbons, and you need sunlight. All right? So those are the important things that will come together to give you photochemical smog. So it's going to be option C in this situation. All right, so T is an element in period 3. The first ionization energy of T is lower than that of the element with 1 less proton. And the oxide of T does not react with water. What is the identity of T? What element is T? All right, so over here, we can identify 2 elements in period 3, which have a first ionization energy that is less than the element before. All right. And I will just summarize this by looking at those 2 elements. All right. So the first part of the electronic configuration, I will shorten this to Ne. All right. And then after this, you can have 3s2. All right. And then the next element will have Ne, 3s2, 3p1, right? Now over here, the outermost electron is slightly more shielded by the 2 3s electrons. And so, and it's also further away from the nucleus slightly. And so that is why it will have a lower first ionization energy. Now this is the electronic configuration for magnesium. And this is the one for aluminium. All right. Now, aluminium has a lower first ionization energy than the element before it, with 1 less proton. This has 12 protons, and aluminium has 13. And the oxide of T, which is aluminium oxide, Al2O3, does not react with water. That is true because aluminium oxide is a hard, non-porous substance, right? It is very unreactive. And so I'm going to go with aluminium over here. All right. And the other options just do not fit. Because sodium oxide does react with water, right? And silicon oxide, well, it does not react with water, but it has a higher first ionization energy than aluminium because silicon is the next element, right? has an electronic configuration of Ne, 3s2, 3p2. Same subshell and same principal quantum shell. So as aluminium, add one more proton, so that means greater attraction, so higher first ionization energy. And for sulfur, well, it does have a lower first ionization energy than the element before it, phosphorus, but its oxide does react with water. So we're going to go with aluminium. All right, now finally on to the organic chem. Let's go. So over here we have tartaric acid, and we have some statements about it. It says a molecule of tartaric acid has more than one chiral center. All right, let's take a look. So over here, we can consider these two carbon atoms over here, all right, because they're not involved in any double bonds. Now this carbon atom over here is bonded to an OH, a hydrogen, a carboxylic acid group over here, and it is also bonded to a CHOH CO2H group, which is different from all the other three groups, and so this is going to be chiral. And similar situation for this other carbon atom over here, so this is also going to be chiral. So yes, a molecule of tartaric acid does indeed have more than one chiral center. The molecular formula of tartaric acid is C4H4O6. All right, let's take a look at this one. So we have 1, 2, 3, 4 carbon atoms, yes. And we have 1, 2, 3, 4, 5, 6 oxygens, right? Now it's just about the hydrogens over here. So we have a hydrogen in the carboxylic acid group, so that's 2, all right. We have an OH group over here, so that's one more, and one more over here, this other OH group. And we have the H atoms bonded to the two chiral carbons, so that's going to be 6. All right. So we have 1, 2, 3, 4, 5, 6. So that's 6 hydrogens, not 4, and so the statement is incorrect. So you can see over here that statement 2 is involved in all first 3 options, so they're all going to be incorrect. So we're only going to go with option D. Just to verify, it says one molecule of tartaric acid produces 4 hydrogen ions in aqueous solution. That's not the case. It's only going to produce 2 hydrogen ions because of the 2 carboxylic acid groups. So carboxylic acid P has no chain isomers. It reacts with an alcohol Q that has only one positional isomer. What could be the ester formed from a reaction between P and Q? All right. So let's take a look at this. We have a carboxylic acid P that has no chain isomers. All right. So what that means is that we could either have ethanoic acid that has no chain isomers, or we could have propanoic acid, because there is no possibility of creating side chains in these situations. You can only create side chains from the carbon atoms that are other than the one in the carboxylic acid group. So when you have just one carbon atom in the alkyl group, or you have just 2 carbon atoms in the alkyl group bonded to the CO2H, you cannot make side chains. So these are the only 2 options available for us. So that means we're left with option A and option C. All right. Now it says over here that it reacts with an alcohol Q that has only one positional isomer. All right. So positional isomer is the positioning of the functional group, right? Now if I look at butanol, I have CH3, CH2, CH2, CH3, that is butane. Now I can place the OH by replacing one of the hydrogen atoms on carbon atom number 1. All right, this would become CH2OH over here. Or what I could do is I could replace one of the hydrogens on the second carbon atom with an OH. So that would be either butad 1-ol or butad 2-ol, right? So butad 1-ol has only one positional isomer of itself, which is butad 2-ol. All right. Now, if I were to go with the pentanol over here, we could have pentad 1-ol, 2-ol, or 3-ol, right? So there are two positional isomers of the original pentad 1-ol. So I'm going to go with option A in this situation. Now over here, which pair includes a hydrocarbon without a chiral center? All right, so this is going to be tough. Let's take a look at this. All right. So over here, I can see that. I'm going to be looking at the carbon atoms in each chain that is not automatically bonded to two or more hydrogen atoms, right? So I'm going to look at just this carbon atom over here. Now it is bonded to an H, a CH3, a CH2CH3, and a CH3CH2CH2. So this is chiral, right? Now over here on this side, I have this carbon atom. Now this is bonded to two CH3s, one over here and one over here, so I'm not going to consider this. Now what about this one? I have bonded this to hydrogen, a CH3, an ethyl group, and whatever this is, right? So obviously all four groups are different, so this is going to be chiral, right? So option A is out. Now let's look at option B. We consider this carbon atom over here. It's bonded to hydrogen and ethyl, methyl, and propyl groups. So this is chiral. Then over here, we look at this carbon atom. Now this is bonded to hydrogen, methyl, ethyl, and once again, propyl. So again, this is going to be chiral. All right. By the way, these two structures are actually the same molecule. So option C, look at this, bonded to a hydrogen, methyl, ethyl, and propyl once again. So this is chiral. And we look at this other structure over here. Now, this is not going to be chiral because it's bonded to two methyl groups over here. And if I look at this one, this is bonded to hydrogen, methyl, ethyl, and whatever this group is, right? And so this is going to be chiral. So we have finally worked our way down to option D. So this must be the option that contains a hydrocarbon without a chiral center. Let's see which one of these it is. So over here, we have a carbon that's bonded to a hydrogen, a methyl, an ethyl, and this group over here. And so this is a chiral center. All right. This is not going to be chiral over here because it is bonded to two methyl groups. Now, this is the hydrocarbon that has been bothering us, right? So this carbon atom over here that's not automatically bonded to two or more hydrogens, it's not chiral because it's bonded to two methyl groups. And this carbon is also bonded to two methyl groups. So this is actually the achiral hydrocarbon. Finally got to it, right? Sometimes MCQs are this maddening. You have to work through all the options and finally you get to the answer. But that's how it is. All right. So what is the major product formed when compound R is warmed with an excess of HBr? All right. So let's take a look at this. Okay. So the thing is that compound R contains two functional groups, the double bond and the alcohol groups. Okay. So the double bond will obviously react. All right. And we need to be careful of the positioning of the bromine over here. Remember Markovnikov's rule? This carbon atom over here is bonded to one hydrogen atom, and this carbon atom is not bonded to any. And so this is where the hydrogen atom ends up once the double bond breaks, and the bromine will be here. So that eliminates options B and D. Now we're left with options A and C. Now over here, the only difference between them is whether the OH will react with the HBr. All right. Now remember that when we convert alcohols into halogenoalkanes, we can actually use the hydrogen halide to do so. And so the OHs will actually react with the hydrogen bromide, and you will get bromine atoms in their place. So option A is going to be correct here. All right, so we have cis-butene that reacts with cold dilute acidified potassium manganate 7 solution to give product X. All right, so we know that when we have cold dilute KMNO4, we're talking about an alkene over here, and this is going to give us a diol. All right. Now, cis-butene reacts with hot concentrated acidified potassium manganate 7 to give product Y. All right, so when we have hot concentrated KMNO4, we know that the double bond will rupture. And so we will get different products depending on what the carbon atoms in the double bond are further bonded to. So let's just draw the structure of cis-butene, right? So we have 4 carbon atoms, right? And we have the double bond at carbon atom number 2. And we have a CH3 here, CH3 over here. And we have hydrogen atoms bonded to each of the carbon atoms in the double bond. So we have cis-butene. The hydrogens are on the same side of the double bond, right? So when this double bond ruptures, right, we can see that this is a symmetrical alkene. So we're going to get the same product on both sides. Now the carbon in this situation over here, it is bonded to a carbon and a hydrogen. So this will be oxidized to an aldehyde followed by a carboxylic acid. And that carboxylic acid ends up being ethanoic acid. So this CH3C now will form a double bond with an oxygen, and it'll form a bond with an OH eventually. So this is ethanoic acid on both sides. So that is actually going to be your product Y. And product X, the diol, is pretty simple enough to draw. We have CH3, CH. Each carbon atom in the double bond will have an OH bonded to it now. The double bond gets converted into a single bond. So we have this. Now this over here is actually a diol. We can name this using the number of carbon atoms in the main branch, which is 4. So that's going to be butane, or we could say butane 2,3 diol. Because we have the 2 OH groups, so that's diol, and they are bonded to carbon atoms number 2 and 3. So butane, or butane, 1, 2, 3 diol. It's going to be 2, 3 diol over here. Okay, so this was product X. Now let's talk about products X and Y. It says when sodium metal is added to separate samples of X and Y, X has the OH group, so these will react with sodium metal, and Y has the carboxylic acid group, so that will also react with sodium metal, right? So both X and Y will react. Now, when sodium hydroxide solution is added to separate samples of X and Y, we know that alcohols are not acidic enough to react with sodium hydroxide, but Y, the carboxylic acid, definitely will, right? So we will say that only one of X and Y will react. All right, and that we know that for sure it's going to be Y that reacts with sodium hydroxide. So it's going to be option B. All right, so for which reaction will the major organic product have the lowest relative molecular mass? Okay. All right, so over here we have bromoethane in the first 2 options that is reacting with aqueous solution of sodium hydroxide. So we know that bromoethane will be converted into ethanol. the bromine will be replaced by an OH. This is a substitution reaction because this is aqueous sodium hydroxide. So we're going to get CH3, CH2, OH. All right. Now, when bromoethane is heated under reflux with the solution of sodium cyanide and ethanol, we have ethanolic NaCN, right? And that means the Br, or the bromine, will be replaced by a cyanide ion. All right, the bromide is replaced by cyanide, so we get a nitrile. So that will be CH3, CH2, Cn. So that's nitrile. Now over here, the CH3, CH2 group is the same, so I don't need to find the MR of these guys. I can just compare the MR of the OH and the Cn. So for OH, it is 16 plus 1, that's 17. For Cn, that is 12 plus 14, so that is 26. So we want to find the lowest relative molecular mass. All right, so option B is already out. Okay, and now option C and D. We have two bromopropane now. So we have a larger halogenoalkane to start out with. This doesn't look very good for these options, but let's try them out anyway. So 2-bromopropane is heated under reflux with an aqueous solution of sodium hydroxide. Now in this situation, again, the bromine will be replaced by OH, right? This is aqueous solution of NaOH. And so we have 3 carbon atoms over here. In the alcohol, that's going to be propan-2-ol. So if I compare ethanol and propan-2-ol, obviously, ethanol will have a lower MR. And so I'm going to not even consider this guy. But option D, now this is interesting. It says 2-bromopropane is heated under reflux with concentrated ethanolic sodium hydroxide. So this is going to be an elimination reaction, unlike the other examples. And so what will happen is that you have CH3, all right? Now the C in the middle was the one bonded to bromine, so the bromine will be gone, and it was bonded to a CH3 group over here. Hydrogen from that neighboring carbon atom will be removed, and you will get a double bond here. So you get propene out of this. What's the MR of propene over here? You can easily compare this. This is going to be 3 times 12 for the carbon atoms, plus we're going to have, okay, by the way, this is supposed to have a hydrogen over here as well. All right. So we have 3 carbon atoms, and we have 6 hydrogen atoms, so that's plus 6. So this turns out to be 42. All right. And for the ethanol, now CH3, CH2, this is going to be 2 times 12 for the 2 carbon atoms, plus 5 for the 5 hydrogen atoms, so that is 29. So when you add up 29 and 17, you're going to get an MR, which is 46. So in this situation, option D wins. So this just goes to show you that you have to go through all the options. You cannot eliminate options and just go with one that suits you in the middle. You have to analyze all the options first and then eliminate systematically. All right, now over here, we have C4H9Cl that reacts with warm dilute aqueous sodium hydroxide. All right, and this is again aqueous, so this is going to be a substitution, just like we were seeing in the previous question. And the Cl will be replaced by an OH. Then it says which isomer of C4H9Cl will form the most stable cation intermediate. Right, so when we talk about most stable cation intermediate, we have to talk about a tertiary carbocation, right? And so that comes from a tertiary halogenoalkane. All right, so for a tertiary halogenoalkane, we have to make sure that the chlorine is bonded to a carbon atom that is also bonded to a side chain, right? And that carbon atom has to be in the middle of the main branch. Okay, so 1-chlorobutane and 2-chlorobutane, well, 1-chlorobutane was simply primary, right? Because the chlorine is bonded to a carbon atom at the end of the chain, so that's going to be primary. Now over here, the chlorine is bonded to a carbon atom in the middle of the main branch or the straight chain. There is no side chain. So this is, the first option was primary, the second option is secondary, right? So again, get rid of this. Now option C and D. Now let's take a look at the structure. Now this is methyl propane, so you have 3 carbon atoms in the main branch. And we have a methyl group bonded to the second carbon atom, right? And now it's saying that chlorine could either be bonded to this carbon atom or this carbon atom, right? So now in this situation, when chlorine is bonded to this carbon atom over here, the rest of the bonds are going to be with hydrogen and this one carbon atom here. So this is going to be a primary halogenoalkane. But if I consider this chlorine over here, this is bonded to a carbon, it's further bonded to 1, 2, 3 carbon atoms. So this is going to be our tertiary halogenoalkane that gives us a tertiary carbocation, and that is why we're going to prefer the SN1 mechanism of substitution here. So option D is correct. All right, so now over here we have 1 mole of an organic compound J that requires 6 moles of oxygen for complete combustion. Right. So let's take a look at this question. It says 1 mole of J reacts with sodium, producing half a mole of a gas that gives a pop with lighted split. All right. So 1 mole of J reacts with sodium and it gives you half a mole of a gas that gives a pop with a lighted split. So that means that J, this gas over here, that gives a pop with a lighted split, this is obviously hydrogen. And so there are only 2 functional groups that react with sodium to give you a hydrogen gas. That could either be alcohol or carboxylic acid. All right. So then it says J reacts with an excess of hot acidified potassium manganate 7 to produce an organic compound, which gives an orange-red precipitate with 2,4-DNPH reagent. Now, the very fact that it's reacting with potassium manganate 7 means that it cannot be a carboxylic acid because carboxylic acids do not get oxidized. It has to be an alcohol. And what type of alcohol? Has to be either primary or secondary. All right. And then it says produce an organic compound which gives an orange-red precipitate with 2,4-DNPH reagent. Now over here, remember that the reaction is happening with an excess of KMNO4. A primary alcohol will be oxidized to an aldehyde, but the aldehyde will not stick around for long enough. When you have an excess of KMNO4, it's going to go up to a carboxylic acid. And we know that carboxylic acids do not react with 2,4-DNPH. So that the answer is a secondary alcohol, and this, upon oxidation, produces a ketone. It's the ketone that gives you the orange-red PPT, or precipitate. Right. So using all of this information, we have found out that J is a secondary alcohol. So which options can we eliminate over here? All right. So over here, butadiene is obviously out because does not react with sodium metal. All right. Butan 2-ol. Now the OH is bonded to a carbon atom in the middle of the straight chain, and there are no side chains. So yes, this is in fact going to be secondary. Propan 2-ol. also is a possible option. 2-methyl propad to all. Now let's take a look at the structure. We have 3 carbon atoms in the main branch, propad. The OH is bonded to the second carbon atom, to all. And then 2-methyl means you have a methyl side chain bonded to the same carbon atom in the middle. So this, the carbon bonded to the OH is further bonded to 1, 2, 3 carbon atoms. So this is tertiary. So this is not going to work. All right. So we have 2 options to choose from. Now we have to look at the information that is given to us. All right. So it says that 1 mole of J reacts with sodium, producing half a mole of gas. Now that is true for both options because both of them have 1 OH group. And what happens then is when you have 1 mole of the alcohol with 1 OH group, the H from the OH group will be removed as half a mole of hydrogen gas. So it's true for both. So you have to look at statement 1. So it says 1 mole of an organic compound J requires 6 moles of oxygen for complete combustion. Right. So let's take a look at option C. Right. So this is propad 2-all. So the molecular formula would be something like C3H7OH. This reacts with oxygen, and complete combustion gives us 3 moles of carbon dioxide, and it's going to give us 4 moles of water. Right. Now, in this situation, we have 6 oxygen atoms over here and 4 oxygen atoms over here. So that's 10 on this side. All right. We already have 1 over here, and so we need 9 more. So this is going to be 9 over 2. So that is 4.5 moles of oxygen. So it cannot be option C. It has to be option B. So just to verify, what we could do over here is C4H9OH. When this reacts with oxygen, you get 4 moles of carbon dioxide, and you get 5 moles of water. And we have 8 plus 5, that's 13 oxygen atoms. 1 of them is already here in the OH, so we need 12 more, so that's 6 moles of oxygen gas. And so it is indeed option B. All right, so now we have an isomerism question, and we need to consider both structural as well as stereoisomerism. Right, so we have an alcohol over here, 3-methyl hexane 3-ol, that reacts with hot concentrated sulfuric acid and forms several isomeric compounds with the molecular formula C7H14. Now this smells of an alkene. And the reason is that alcohols, when they react with hot concentrated sulfuric acid, this turns out to be a dehydration or elimination reaction. All right. So now looking at the structure, we have different areas from which we can remove hydrogen atoms and draw a double bond. So this carbon atom is the one that is bonded to the OH. Now this OH will be gone. Now this carbon is further bonded to 1, 2, 3 carbon atoms. All right. So if I consider this first carbon atom over here, if a hydrogen is removed from here, then the skeletal formula becomes something like this. You have a double bond here, then this carbon is bonded to a CH2CH3, and then it is bonded to a CH2CH2CH3. Now this is an alkene over here. Now, whenever there's a double bond involved, I'll automatically think about cis-trans or geometrical isomerism. Now the problem over here is that this carbon atom over here is bonded to 2 hydrogens, and so we will not consider it in this example. So this is one isomer. All right. Now, if I consider removing a hydrogen atom from this carbon atom, then I will have a double bond over here. Now, the first carbon is bonded to a CH3, and this carbon atom is also bonded to a CH3. but this is further bonded to a CH2, CH2, CH3. Now over here you can see that each carbon atom is bonded to two different groups, CH3 add propyl, and over here methyl add a hydrogen. So this is actually the cis isomer, all right? And we can also have the trans isomer, and so this will give us two alkenes, all right? Now, if we consider this carbon atom over here, the double bond is oriented like this, and we're going to have a CH2, CH3 over here, and on the other side also a CH2, CH3, and a CH3 over here, and this is bonded to a hydrogen. So around this double bond, you can see that we have CH2, CH3 groups on opposite sides, right? And so this is the trans isomer that I've just drawn. And we can also have a cis isomer because each of the carbon atoms in the double bond are further bonded to different groups. So we have two isomers over here. Add these numbers up, you get 5. Right. Now over here we have some compounds and some tests run on them. All right. Now it says which rows show the correct predictions. All right. So for the first compound, this is just simply ethanol. All right. It will actually give you a pale yellow precipitate with alkaline aqueous iodine. So this is correct because of the presence of the CH3 C double bond O group over here. It's further bonded to a hydrogen. This is ethanol. Felling's reagent, yes, it will give you a red precipitate because this is an aldehyde. All right. And with Tollens reagent, same result. So row 1 is in fact correct. So that eliminates option D. Then we have propanone over here. CH3CO, CH3. Obviously, because this is a ketone, it will not give you any result with Felling's and Tollens reagents, but with alkaline aqueous iodine, it will give you a pale yellow precipitate because of the presence of that same CH3 C double bond O group. So row 2 is also correct, so that eliminates option C. Now, the final one, the one that will decide our fate. So we have over here pentan 3-one. All right. Now over here, because it's a ketone, it will not give you any result with Felling's or Tollens reagents. And with alkaline aqueous iodine, it will not give you a result either because the C double bond O is not bonded further to a methyl group, a CH3. And so option A is going to be correct. All the predictions are correct. Right. Now, which mechanism describes the reaction of aldehydes and ketones with hydrogen cyanide and sodium cyanide? Now, remember, guys, the only mechanism that you have studied involving aldehydes and ketones is nucleophilic addition. I'm not going to go into the details of how this works, and you need to save time. And we've already spent way too much time on this paper anyway. So I'm just going to go ahead with this. This is an easy question, a gimme, boom, easy as that. All right, so we have propyl propanoate, an ester that's been made using propane nitrile using 3 steps. So we have propane nitrile over here. So in step 1, it's been converted to compound X. In step 2, it's been converted into compound Y. And then in step 3, what happens is Y is going to react with more of compound X to form the propyl propanoate. Right. So which reagents are suitable for carrying out step 1 and step 2? So what we can do over here is we can convert propane nitrile into propanoic acid, and that will be done using hydrolysis. What will happen is the C triple bond N is going to break, and with the help of water and an acid catalyst, we can convert these guys into ammonia and the carboxylic acid. So you're going to get propanoic acid out of this, and that's going to be your compound X. So we're going to do acid hydrolysis over here. If we did alkaline hydrolysis, the carboxylic acid group will convert into a salt rather than the acid. So step one, we're going to consider either option A or option B, a strong acid catalyst for the hydrolysis. Now, compound X is going to be converted into compound Y, and then compound Y will react with more of X. Now we know that X over here is the acid, right? And Y then has to be an alcohol. And it says over here that we can use some of X, some portion of X, and convert it into Y, the alcohol, which will react with the rest of the acid X to give you propanoate. So how do we convert the carboxylic acid into an alcohol? The simple solution is reduction, right? So what happens is that the oxygen gets bonded to hydrogen atoms gained from the reducing agent, and this will bond to two hydrogens of its own, and it's going to form an alcohol. The propanoic acid will make propanol, specifically propan-1-ol, because carboxylic acids get reduced to primary alcohols. So out of these two options, only LiAlH4 is a viable reducing agent. We need a strong reducing agent to convert the carboxylic acid into an alcohol, and so option B is going to be correct. All right, so we have an ester over here that is hydrolyzed by boiling with aqueous sodium hydroxide. So this is alkaline hydrolysis. Which compound is one of the products? So what we can do over here is we have the structural formula, and we can split it over here. So this part is going to be the acid part, and this actually ends up reacting with the excess sodium hydroxide. It's going to give you a salt. So that's going to be CH3, CH2, CO2. Well, originally would have been H over here, the carboxylic acid, but now it's going to react with sodium hydroxide. So I'm going to have Na over here. So this is sodium propanoate. All right, so that's option D over here. The other product from the alcohol part, this is going to bond with the OH, and that's going to give us methanol. And that's not either of the options. So we have a compound V that polymerizes to form polymer W, right? So what is the correct name of compound V? All right, so in order to solve this question, we have two carbon atoms over here that are next to each other in the main branch of the polymer, right? So I'm going to segregate these, all right? And so we have two carbon atoms over here. You're going to form a double bond between them now, because this is the monomer we're talking about. The first carbon is bonded to two chlorines. The second carbon is bonded to one chlorine and one CH3 over here, right? And you can see that the same pattern repeats for the second pair of carbon atoms and the third pair, all right? Now over here, the longest carbon chain has 3 carbon atoms in it. So this is going to be propene, right? So the only option that refers to propene is over here, right? And just to confirm, we have 3 chlorines, so this is trichloro, right? And we have the chlorine atoms at carbon atom number 1, 2 of them. And at carbon atom number 2, we have 1 more chlorine, so it's going to be 1, 1, 2. Trichloropropene, that is going to be the compound V. And finally, we have a question on infrared spectroscopy. All right. So it says a molecule of an organic compound P contains 3 carbon atoms and shows a strong absorption at 1720 per centimeters in its infrared spectrum. All right. So if you look down at this table, 1720 appears to be within the range of C double bond O. All right. It is within this range and within this range. So we cannot tell for sure which C double bond O this is. Let's look at the remaining question. It says P is reacted with an excess of hot acidified potassium dichromate 6, forming organic product Q. All right. So we know that P has a C double bond O. That's for sure. And Q, basically it has a strong absorption at 1700 per centimeters and a strong broad absorption centered at 2800 per centimeter. All right. So for 2800 per centimeter, that falls within this range. So that is the OH bond in a carboxylic acid group. And the 1700 per centimeter, well, that falls within this particular range. All right. And that is the C double bond O in either carbonyl or carboxyl. All right. So I'm going to go with carboxyl over here. All right. And because it just matches with the OH over here, that belongs to a carboxyl, so the C double bond O must also belong to the carboxyl group. So it has a C double bond O, OH. So that's what Q contains. All right. So we know that P is oxidized to Q that contains this carboxylic acid group. All right. And P only has the C double bond O. Right. Now, we know that out of all this compounds containing C double bond O, it's only the carbonyl compounds that can be oxidized, and specifically aldehydes are oxidized by K2Cr2O7 as given in this question. And so we need to find an aldehyde containing 3 carbon atoms, all right? And so that has to be option A. All right, now finally we are done. This was the October-November 2022 paper 1 variant 2 of the AS level chemistry syllabus, and you have just completed the entire explanation of that most recent paper. And with this, if you enjoyed this video, please leave a like, do comment if you have any further questions, and do subscribe to the channel. And I'll see you in the next video.